For decades, the United States built the world's most sophisticated satellites. It designed spacecraft that could survive the freezing darkness of space, the blistering heat of direct sunlight, and radiation powerful enough to destroy ordinary electronics. Yet today, one of the materials that quietly makes those missions possible comes from a supply chain Washington doesn't fully control anymore. That's a strange sentence to say about a country that put humans on the moon. When people think about strategic resources, they usually imagine oil fields, lithium mines, or semiconductor factories. Those industries receive headlines, government funding, and political speeches. But hidden underneath almost every advanced satellite is a class of engineering ceramics so specialized that losing access to them doesn't merely increase costs, it changes what can be built. The material isn't famous. Most people have never heard its name. Even within aerospace, it rarely gets public attention because it's buried deep inside components that nobody sees. Yet, without it, satellites struggle to manage extreme temperatures, high-frequency communications become less reliable, and certain radar systems simply cannot perform as designed. Here's the question that caught my attention. If the United States pioneered much of this technology, why is China spending enormous efforts securing nearly every important source of the raw minerals needed to manufacture it? The answer begins thousands of kilometers away from any launch pad. It begins in mines. Not rocket factories, not satellite assembly plants, just mines. The ceramic family we're talking about includes advanced materials like high-purity alumina ceramics, and even more critically for aerospace, ceramics derived from exceptionally pure rare earth elements and specialty minerals used in dielectric components, thermal barriers, and precision electronics. These aren't decorative ceramics like coffee mugs or bathroom tiles. They're engineered atom by atom to survive conditions that destroy steel, aluminum, or even titanium. One satellite can contain dozens of ceramic components performing entirely different jobs. Some electrically isolate sensitive electronics. Others protect sensors from heat. Some guide microwave signals with incredible precision. Others survive repeated thermal cycles between roughly -170 degrees Celsius and well above 120 degrees every orbit around Earth. Nature doesn't hand over these materials ready to use. First, someone has to mine the right minerals, then refine them to extraordinary purity, then manufacture them under conditions where microscopic contamination can ruin an entire production batch. That's where geopolitics quietly enters the story. Over the last 20 years, China wasn't simply building ceramic factories. It was securing upstream control over the raw materials feeding those factories. Chinese companies invested in mining projects across Africa, expanded domestic extraction, strengthened refining capacity, and acquired influence over mineral processing that many Western governments considered too ordinary to worry about. Ordinary turned out to be expensive. There's a lesson history keeps repeating. Countries often focus on glamorous technologies while ignoring the supply chains underneath them. Building satellites attracts television cameras. Opening a mineral processing facility usually attracts accountants. Ironically, accountants sometimes end up deciding military capability. That's not entirely a joke. The Pentagon can fund revolutionary spacecraft, but if critical ceramic powders depend on fragile overseas supply chains, engineering brilliance alone doesn't solve the problem. To be fair, America isn't without options. It still possesses world-class research institutions, leading ceramic manufacturers, and some of the planet's most advanced aerospace companies. Supporters of the current strategy argue that trusted allies can supply many critical minerals, while domestic production gradually expands. There's truth in that argument, but it also assumes those alternative supply chains already exist at sufficient scale. In several cases, they don't, or they're still years away from meeting future demand. That difference matters because satellites are no longer just scientific instruments orbiting peacefully above Earth. They're communication networks, missile warning systems, navigation platforms, weather monitors, intelligence collectors, and, increasingly, the backbone of modern military operations. Control the materials behind them, and you quietly influence far more than manufacturing. My own view is that governments spent years debating who could build the smartest satellite, while paying surprisingly little attention to who controlled the ingredients. That feels like designing the world's fastest race car, without asking who owns the only fuel station. And here's where the story becomes even more interesting. Because the ceramic material itself isn't the rarest thing in this entire equation, the processing technology, and the handful of mines producing exactly the right minerals, may be even more important. The first country to truly understand the strategic value of advanced ceramics wasn't necessarily the one that invented the best versions of them. It was the one that realized the supply chain begins long before the laboratory. That distinction matters. During the Cold War, the United States poured enormous resources into ceramic science. NASA, the Department of Defense, and institutions like the Oak Ridge National Laboratory funded research into materials that could survive impossible environments. Ceramic matrix composites, ultra-high purity alumina, silicon carbide, and specialized dielectric ceramics became essential for spacecraft, missile systems, and high-frequency electronics. America led the science. Industry followed. For years, that seemed enough. Meanwhile, China was watching a different part of the equation. Around the early 2000s, Beijing began treating critical minerals as long-term strategic assets rather than ordinary commodities. The Ministry of Natural Resources, together with state-backed companies and provincial governments, encouraged investment not only inside China, but across Africa, Central Asia, and parts of South America. Much of the attention focused on rare earth elements because they attracted headlines, but another layer of the strategy received far less publicity: specialty industrial minerals. High-purity bauxite, certain grades of kaolin, magnesite, zircon-bearing deposits, and several obscure materials used as feedstock for advanced ceramic production. Each mine, viewed alone, looked insignificant. Together, they formed something much larger. Think about satellite manufacturing like baking a wedding cake. Everyone admires the decoration at the end. Almost nobody asks where the flour came from. Yet if one supplier controls most of the world's premium flour, the bakery becomes less independent than it appears. The same logic applies here. Take high-purity alumina as one example. Producing ceramic-grade material isn't simply a matter of digging ore out of the ground. The refining process removes impurities measured in parts per million, because even tiny contamination can change electrical behavior or reduce thermal performance. Aerospace manufacturers often reject entire production lots over defects invisible to the human eye. That level of precision creates a bottleneck. Building another refinery isn't impossible. Building one that consistently produces aerospace-grade material at commercial scale is much harder. This is why processing deserves as much attention as mining. China gradually expanded both. By the late 2000s, Chinese companies had become deeply involved in refining capacity that supported industries ranging from electric vehicles to aerospace ceramics. Western manufacturers still possessed exceptional engineering expertise, but many increasingly depended on internationally distributed raw materials, whose processing chain often passed through China at some point. Notice the difference. Dependence doesn't necessarily mean monopoly. It means leverage. Those are not the same thing. The United States still imports significant quantities of critical minerals from trusted partners like Australia and Canada. Supporters of globalization argue that's perfectly normal, because modern manufacturing has always relied on international trade. They're right, to a point. The weakness appears when one country dominates several stages of the chain simultaneously: mining, refining, chemical processing, intermediate powders, industrial-scale manufacturing. Each stage individually looks manageable. Combined, they become difficult to replace quickly. We've already seen this pattern elsewhere. During recent supply chain disruptions, industries ranging from automobiles to consumer electronics discovered that relatively inexpensive components could halt production lines worth billions of dollars. Sometimes, A factory wasn't waiting for sophisticated technology. It was waiting for a part costing only a few dollars. Strategic materials work the same way. A satellite worth hundreds of millions of dollars can be delayed because one specialized ceramic component isn't available on schedule. That's an astonishing imbalance. There's another overlooked factor. Advanced ceramics rarely serve just one industry. The same materials used inside communication satellites may also appear in missile guidance systems, semiconductor manufacturing equipment, hypersonic research, medical imaging devices, nuclear energy projects, and next-generation telecommunications infrastructure. One supply chain, multiple national priorities. That's exactly why governments have started paying closer attention over the past few years. In Washington, agencies including the Department of Energy and the Department of Defense have launched initiatives aimed at strengthening domestic critical mineral production and expanding processing capacity. The European Union has introduced similar policies through its Critical Raw Materials Act, recognizing that manufacturing leadership means little if upstream resources remain vulnerable. Whether those efforts arrive soon enough is another question entirely, because while new policies are being announced, China's strategy has already been unfolding for more than 2 decades. Time, in industrial planning, compounds much like interest in a bank account. And when we look closely at one seemingly ordinary mine, we'll see how that quiet head start turned into influence reaching all the way into orbit. People often imagine geopolitical competition as a race between laboratories. It isn't. More often, it's a race between supply chains. And this is where the story becomes more complicated than simply saying, China controls the mines. In reality, China doesn't own every important deposit. Australia still has significant reserves. Brazil, India, South Africa, Vietnam, Canada, and several African nations produce many of the minerals needed for advanced ceramics. The real advantage comes from connecting those mines to refining plants, chemical processors, manufacturers, and export networks that already exist. Owning a mine is valuable. Owning the ecosystem around the mine is far more valuable. Take zircon as an example. It doesn't receive the same attention as lithium or rare earths, but high-purity zircon is indispensable for many advanced ceramic applications. Australia remains one of the world's largest producers, yet a substantial portion of processing and downstream manufacturing eventually moves through Asian industrial networks, where Chinese companies have built enormous capacity over decades. The same pattern appears with several other specialty minerals. This is the reversal that surprised me. For years, policymakers worried mainly about where minerals were extracted. The more decisive question may actually be where they're transformed. Because raw ore isn't what satellite manufacturers buy. They buy engineered powders with precisely controlled particle sizes, ultra-pure ceramic substrates, specialized dielectric components, materials certified to survive years in orbit without degrading. Each additional processing step filters out competitors who lack the technology or industrial scale. That creates a barrier which isn't visible on a map. Let's make this practical. Imagine 2 countries discover identical mineral deposits tomorrow. Country A has mines but no refining industry. Country B has refining plants, chemical engineers, equipment manufacturers, quality control laboratories, logistics networks, and customers already waiting. 5 years later, which country dominates the market? Usually, it's not the one with the bigger mine. It's the one with the stronger industrial chain. That explains why rebuilding supply security is taking longer than many expected. The United States recognized this vulnerability well before recent headlines. Reports from the U.S. Geological Survey, the Department of Energy, and successive National Defense Authorization Acts have repeatedly identified critical minerals as national security priorities. More recently, the Inflation Reduction Act and the CHIPS and Science Act encouraged domestic manufacturing and strategic investment across multiple technology sectors. Critics sometimes dismiss these policies as industrial protectionism. Supporters argue they're overdue. Personally, I think both sides have part of the story. Markets are extraordinarily efficient until national security enters the conversation. Companies naturally buy from whoever offers the lowest cost and most reliable delivery. Governments, however, must prepare for situations where those assumptions suddenly disappear. The pandemic offered a painful reminder. A shipping delay on one side of the world interrupted factories on the other. Imagine applying that lesson to satellites, missile defense, or secure military communications. The consequences become much larger. There's another misconception worth challenging. Some commentators frame this as a zero-sum contest, where China's gain automatically means America's permanent decline. Reality is rarely that simple. The United States still leads in many areas that matter enormously: aerospace engineering, satellite design, precision manufacturing, advanced research universities, and defense innovation. Those strengths remain substantial. But strengths at the top of the supply chain don't automatically erase weaknesses at the bottom. That's the uncomfortable balance policymakers are trying to solve. Remember the opening question: how could the country that pioneered so much ceramic technology find itself worrying about mineral access? The answer isn't technological failure. It's strategic timing. While much of the West optimized for efficiency, China optimized for resilience. Those goals sound similar until a supply disruption occurs. Efficiency minimizes today's costs. Resilience accepts higher costs today to reduce tomorrow's risks. Only afterward do you discover which strategy was better. We're already seeing governments respond. Australia is expanding critical mineral partnerships with the United States and Japan. Canada is investing heavily in processing capacity. The European Union is funding new refining projects to reduce dependence on external suppliers. None of these initiatives would exist if leaders believed the market could solve everything on its own. Yet industrial ecosystems aren't built overnight. A mine may take a decade to permit. A refinery can require years before producing commercial volumes. Training engineers takes even longer. That's why the decisions made 20 years ago are shaping satellite programs today. And looking ahead, the next battle may not be over who owns the richest deposit. It may be over who can build an entirely different supply chain before the current one becomes a strategic liability. For all the attention paid to satellites, missiles, and artificial intelligence, I keep coming back to something much less glamorous: a bag of ceramic powder. That sounds almost ridiculous until you realize that without the right material, some of the most sophisticated hardware ever built simply doesn't leave the factory. History has a habit of reminding us that power rarely depends on a single invention. More often, it depends on thousands of invisible decisions made years earlier. Which mine to develop? Which refinery to build? Which supply chain to protect? By the time a satellite reaches orbit, the real competition may have been decided a decade before the rocket ever ignited. That's why this story isn't really about ceramics. It's about strategic patience. China's approach wasn't perfect, and it certainly wasn't without cost. State-backed investment tied up enormous amounts of capital. Some overseas mining projects faced political resistance, and not every acquisition produced the expected returns. There were failures that rarely make international headlines. But looking at the bigger picture, one theme keeps appearing. Beijing consistently treated upstream resources as long-term geopolitical assets, rather than short-term business opportunities. The United States, on the other hand, spent much of the post-Cold War period assuming global markets would reliably provide whatever industry needed. For decades, that assumption worked remarkably well. Companies reduced costs, production expanded, and consumers benefited from cheaper technology. Then the world became less predictable. Trade disputes intensified. Pandemics disrupted shipping. Wars reshaped commodity markets. Suddenly, efficiency didn't look quite as secure as it once had. That doesn't mean America has already lost this contest. Far from it. The United States still possesses extraordinary advantages that cannot be replicated overnight. Companies like Lockheed Martin, Northrop Grumman, RTX, Boeing, L3 Harris, and a growing number of commercial space firms continue to produce some of the world's most advanced spacecraft. NASA remains one of the most influential research organizations on Earth, while national laboratories continue pushing ceramic science into areas that barely existed a generation ago. Innovation has never been America's weakness. Scaling secure supply chains has become the harder challenge. Fortunately for Washington, it has begun responding. Investments in domestic critical mineral production, partnerships with Australia and Canada, expanded processing initiatives, and incentives for advanced manufacturing all point toward the same conclusion. Policymakers increasingly recognize that resilience carries economic value. Whether those efforts arrive fast enough remains uncertain. Industrial ecosystems are stubborn things. You can't announce a refinery today and expect aerospace-grade ceramic materials next year. Environmental approvals, construction, engineering expertise, testing, certification, and customer qualification often stretch across much of a decade. Meanwhile, demand isn't standing still. The global space economy continues expanding. Thousands of new satellites are planned for communications, Earth observation, navigation, climate monitoring, defense, and scientific exploration. Every one of those programs adds pressure to supply chains that were already under strain. And here's the prediction I'm willing to make. Within the next 10 years, governments will compete just as aggressively over mineral processing plants as they currently compete over semiconductor fabs. The conversation will shift from who builds the best satellite to who controls the industrial foundation that makes satellites possible. That shift has already begun. Most people simply haven't noticed because supply chains don't produce dramatic headlines. Launches do. Explosions do. Political speeches do. A new ceramic processing facility rarely trends on social media. Yet it may influence the balance of technological power more than another carefully worded summit declaration. There's one final thought I'd leave you with. Every era has a resource people underestimate until it becomes impossible to replace. In the 20th century, it was oil. In the digital age, it became semiconductors. The next chapter may belong to the advanced materials hiding underneath nearly every breakthrough technology we depend on. Sometimes the future isn't limited by the engineers designing tomorrow's machines. Sometimes it's limited by whoever owns yesterday's mine. If you enjoyed this deep dive, I'd love to hear your perspective. Do you think the United States can realistically rebuild these supply chains? Or has China already secured too much of the advantage? Let me know in the comments, and I'll see you in the next one.